No, I'm so excited. Hey, who's static variable? No one in here?
It might be possible.
Oh man, there's a few people jumping into IRC right now. Alright, let's see this. Alright, due to me not knowing how to... Oh, who's Badger?
Yeah.
Alright. Due to me not knowing how to hook my laptop up to this crazy projector array that they have going on, this is literally the stream that's going out over the internet right now. So that's pretty much, it's going from my computer out to the internet where everyone else can see it and then back in here. Pretty sure there's audio too, but out to the internet where everyone else. Yeah, there we go.
Cool.
Alright, another cool thing is when I put Windows up, it just blacks out the video, so I don't have to worry about people seeing what I'm doing. Alright, this is actually the same Ubuntu image that everybody else has. It's just...
I have about half of it.
You have half of it? Alright.
I got the same one last year though.
This is a different one.
Sure.
I threw this one together like last night. Look at that delay.
Are you streaming to the IRC?
If you go to usesigsac.com, you'll get the link to the stream. We're going to start at see 1, 2, 3, 4, 5 seconds. Hey, is Jonathan in here? Alright, Jonathan is the cadet up in Thayer 348. When he shows up, we'll begin. What can we do until then? I know, I was told to put together more flashy things for Sigsac. So, I spent 3 hours this weekend ripping through the source code of WordPress plugins looking for SQL injections. First time I've done this since this time yuck year. I didn't find any, but I made a video where each second of the video is a minute of my life. So it's a 3-minute long video. So we can have video time while we wait. And we'll just do it here. Sir, I'm definitely exciting enough. And everybody watching through IRC can just miss out. I also got what is going to be the official Army Cyber reading list as soon as it gets approved today, my inbox. From Michael Wigan, who's apparently having way too much fun.
Hello?
Michael Wigan, he's a
Oh, Mike, yeah.
2011 grad.
Where did he end up?
He's at Army Cyber right now.
Is that just for the Forest Bullock?
That is, right now it looks like he might not even go to Bullock.
So he's just gonna stay there as
So this is me trying to make sure I got some things right in MySQL, trying to do a select on two tables without using a comma. Couldn't figure it out. I think eventually I gave up and I moved on. And then what I ended up doing is,
Opening some tabs.
yeah, I was trying that for a while. Anyways, what I ended up doing is, instead of going back and forth to like Firefox, I'll just go into the code and I'll have it print out stuff to see where I am, and then I'll just run a quick script, which is just a quick HTTP client, and then see if what I want is coming out. How cool is that? I could have played video games, but instead I audited source code. Only everybody could have had a wonderful, I think this was yesterday, wonderful Monday evening. That's about as flashy as my life gets.
Are you always recording your desktop?
No, I just did it specifically for the flashy value, sir. So this one right here, I was only doing
You get some pretty damning stuff on there.
I was only looking for select statements if you know anything about SQL or SQL. We'll learn more about it later, but if you can even do what's called like a blind SQL injection, which means you don't even get anything back. Sometimes you can do things like you'll have a query, and if the query executes true, then there'll be like a delay, like a half-second delay before it returns a result. And so you can do things like for FluxBB, when they had 1.4 beta 2, they moved to 1.4 beta 3 because of me. They had a thing on their email. So what would happen is they would check your email to see if your email was valid, and if your email wasn't valid, they would say your email's not valid. Then they would take that email and they would check it in the database to see if it already exists. And then if it already existed in the database, they would say this email already exists in the database. And if it didn't exist, they would say it doesn't exist. Well, the problem is that when they checked the email to see if it was a valid email and it was an invalid email, they should have just stopped right there, because they didn't escape the email address when they queried against the database. So you couldn't just get the password of the database. But what you could do is you could say where your email equals something that's not going to be a valid email address, maybe even just an empty string, or password. You say like the first character of the password is A, where the user ID is 1, and then if it says hey, this email address already exists. Or what did you say? Use an email address that already exists in the database. No, one that doesn't exist, or the first letter of the password is A for the administrator. And so if that comes back as true, then the first character of the administrator's password is A. If it comes back as false, then you try the B, and then you try C, and then you try D, and you keep doing all these queries until you get the first character. Then you say, if the first two characters are SA, SB, SC, SD, and so I wrote a script that did it, and over the course of like 600 queries, it would start printing out one character at a time, all the different characters to not the password, but the password hash for like, the administrator of the WordPress blog. It was totally cool to look at. Too bad I don't have it anymore. Sorry. But that probably would have been something nice. Is Jonathan here yet? Alright, let's go. Alright, who was actually able to download the image and get it installed? Anyone?
Yep.
1, 2, 3. Alright. Let's get this. Alright. Those of you who are in the image, are you like booted up into it right now? Alright. So the first thing you want to do is you want to open a command prompt. Don't worry, my colors are different. It's the same thing you have. So you can go to Applications, and then I think Accessories and Terminal, or you can just hold down Control Alt and hit T. So Control Alt T. wait for the 5-second delay. And then you can just hit F11 and that'll make it full screen. Because we're not doing anything that doesn't, well, we might, but, alright. How do you what? What program? VirtualBox. Are you on the Sigsac distro? Like a couple hours ago or today? Alright. Alright, so when we give instructions for Sigsac on how to do stuff, we're never going to give step-by-step instructions on like go to this website, download this file. When you download the file, install the program, then go to File, and then go to Properties, and then select this property. It's really just going to be like download VirtualBox and install this appliance. And we're saying that with the understanding that you probably don't know what VirtualBox is, probably don't know what a VirtualBox appliance is. I mean, a VirtualBox appliance is, they call them virtual machines in other virtualization softwares. Probably never imported or installed a VirtualBox appliance into VirtualBox before, but the assumption is that you'll be able to figure it out. So just, there we go, keep that in mind. Alright, so what you want to do is you want to go to VirtualBox and then just click around until you find import appliance or whatever that is, and then you want to select that file that you downloaded. It's like sigsacbase.ova, should be like 1.5 gigs, and then that's going to start creating a new VirtualBox machine off of that image, and then it'll set it up and it'll be Ubuntu. It'll be fully patched as of last night, and it'll have a bunch of stuff that we use already installed on it, and it'll have what we're going to use today installed on it too. And the reason why I went ahead and just gave everybody an image is because right now codename CRD is still working on getting the West Point network set up so that we are authorized to put stuff on it that we're not authorized to put on it yet. And so in order to stay in compliance with the regulations, instead of giving everybody VirtualBox and having, you know, 50, 20, 100 machines go on the network, I just made an image and sent it out, and so it's already set up. How exciting is that? Great. So who's actually inside the VirtualBox image right now with it running?
I'm in the older image.
All right, a couple people. All right, so you can follow with me and everybody else. Pay attention. All right. So if you're looking at this right here, then there's a folder. Well, how many of you have used Linux before? How many of you haven't used Linux before? All right, let's talk about Linux. Welcome to the shell. All right. So think about it like this. Basically, 90% of the time when we interact with Linux in here, we're going to interact with Linux through a terminal, okay? Terminal is the piece of software, and it pretty much more or less just accepts input from the keyboard, and it sends that input to a program, and the program spits out characters, and that's what the terminal shows, roughly. Inside the terminal, our terminal runs a program called a shell. And so this shell is, I think this is bash, it's bash. So the shell program does all sorts of cool things for us, like it lets us run programs. And so in our shell we type in a command, which is normally a program name. It runs that program, and that program does something, sends the output to the shell, and then the shell, we can do things with that output. 99% of the time we just have it spit it right back out to the terminal and we see it. So with this basic functionality, that's how we interact with Linux. So right now we're sitting in what's called the home directory. So every user has a home directory. It's like your My Documents directory. Well, it's the directory beneath the My Documents directory. So if you want to see what files are in this directory, the command for that is ls. So if you type in ls and hit enter, boom, you see all these files. So everything that's bold and blue is a folder. Everything else is just a file. And then there's other things too you can pass what are called flags or arguments. Slight subtle difference there, what we need to worry about right now. So if you type in ls-tech-l it'll give you more details, and you put a H on there, it'll make all of the file sizes human readable. So it'll say like kilobytes instead of so many bytes. Alright, so we can get into more of that later. Right now we're interested in the Sigsac directory. So to change into a directory, the command is cd. So it's cd, and then the directory name. So you see that squiggly line right there? That's just shorthand for home directory, and then /Sigsac, so that's where we are. And then inside the Sigsac directory, we have two directories. We have Ravm, which is awesome, which we're going to use today, and we have Metasploit, which maybe we'll get to another day. It's already on there. Don't play with Metasploit on the network. Alright, so let's go into Ravm. Alright, so when we look inside the Ravm directory, there isn't a whole lot here. There's a makefile, I think an empty readme that's in there so GitHub will stop yelling at me. Programs and source. So we're going to compile our first program today in Linux. Very excited. Type make, hit enter. Look at that. No warnings, no errors. Well, you'll see it in a second here. Oh man, that's awesome. That's so cool. All right. So now if we type ls again, we'll see that we have compiled these programs. All right, who's confused yet? Who's sort of lost in the sauce a little bit? What did I say that was not, that was... All right, we're good. So the first thing we're going to do is we're going to learn assembly today. So we're going to create a simple assembly program. All right, so go ahead. We'll start up a program called gedit. All right, if you hold down Control-Alt and hit right on your keypad, window right, these are called workspaces in Linux. They're awesome. Right, you can go up to Applications, Accessories, Text Editor. Honestly, I just like to open up a terminal and type in gedit. I think it's faster. All right, here we are. So if you remember from our class last week, we talked about a processor, and we talked about how we have registers, we have memory, and we have instructions. And so the instructions operate in the registers, and then we move registers in and out of memory to do things. Right? Okay. Assembly is how we create those instructions. So we write what we want to happen in assembly. We give that to an assembler, and the assembler takes our text and it transforms it into instructions for the processor. So let's write a program. Let's write a program that adds the number 2 to the number 3. Yeah, let's get excited. So how are we going to do this? We're going to start with the move instruction. All right, we're just going to cover instructions as we go. So we'll start really simple. So we're going to go move. It's just 3 letters. All right. And then our registers here, we have registers 0 through 7. So we have R0, R1, R2, R3, R4, R5, R6, R7. And then we have 2 other registers. We have RSP and we have RBP. And so that stands for stack pointer and base pointer. All right. And then we have other registers that we're not really concerned about. Like there's a flags register and an instruction pointer, but we're not ever going to be manipulating those registers. They're special. All right. So we're going to go move. So we'll pick a register. We'll say R1, R0. Is it R0? I might have to check. Yeah, all right. R0, and then we're going to do 2. All right, so let's talk about this. This assembly language in the Ravm is designed to somewhat mimic how assembly looks like for the x86 CPU. All right, for the Intel, well, it's not really Intel's, it is Intel's, the x86 CPU architecture. That's what all your laptops are running. That's what you're going to encounter in the real world most of the time. All right? And so while this is a simplified version of that instruction set, it's not really as complicated. It's sort of reduced from the instruction set that the x86 uses. It's going to look kind of similar. So when we go from here to x86 assembly, it's not going to be as big a jump as if we were using some other crazy architecture and assembly language. All right? So it's pretty simple. We have our instruction, and then we have the destination, and then we have the source. So that's just R0 equals 2. Everybody with me so far? All right, that's a lot to cover, setting and register to the value of 2. Then we're going to have add R0 3. And then we're going to have a special instruction that we have only for the Ravm. It's going to be halt. And so when we reach the halt instruction, our program will stop executing. Pretty cool. Let's save our awesome program so we can run it. Alright, so we're back in the Ravm directory. Alright. I saved my file right there, class 1 at ASM. Now we're going to send it to the assembler. The assembler is going to take this file and it's going to turn it into these instructions for the CPU. So to do that, it's going to be /assembler, and we're going to know why it's /assembler, not just assembler later. All right, class 1 .bin for binary, and then class 1 .asm, or whatever you want to name them. Doesn't really matter. All right, now we have this file. Pretty cool. Before we run it, I'm just going to run it through the disassembler real quick so we can look at what's in there. What happened to this? Oh. When you disassemble your programs, make sure you're disassembling the binaries, not the text files. Okay. So pretty much what we're looking at here is this. I know we didn't cover what hexadecimal is, but this is just a representation of the actual bytes. So each two of these characters is a byte. Oh, and then this is what the instruction is. And this is what the registers and values are. Okay? We got 3 instructions. This is what they look like in the disassembler. This is the address that they're at. So if our program starts at 0, right? 0, then we have 6 bytes. Here, 1, 2, 3, 4, 5, 6. And so at 6 is where the next instruction is. And then C, which is 12, is where the last instruction is. Yeah, I know. Computers are awesome. All right. Ready to run it?
Where did you save that?
Where did you save it to?
Save it in Sigsac.
Okay, then go. Then here's what we'll do. If you're looking at this right here, /Sigsac/Ravm, type CD and then 2 dots. That'll take you to the directory beneath where you are. Type ls. Tell me if you see that file. No? Let me ask this. Does anyone know why we're learning assembly? No? Alright. Let's talk about this for a minute while they're doing this. Alright. When you guys hear the word hacking, I know we didn't have a big giant philosophical discussion on day one, but when you hear the word hacking, what do you think of? Nothing? You just think silently? Swordfish, Kevin Mitnick. Alright. There seems to be, when people think of hacking, they think about all these cool things that happen, these manipulations, I call them. And so, Metasploit is a program full of manipulations. What Metasploit does is it's full of exploits, which we're actually going to start talking about, if not today, then tomorrow, right, that other people have found and put together into Metasploit. And so if you have a vulnerable piece of software and it hasn't been patched, then there's a chance that maybe there's an exploit for it in Metasploit, and you can use these exploits to take control of that program and do what you want with the computer. And so what happens is that everybody hears about hacking, and they get really interested in all these manipulations. And like, I want to learn about the manipulations. I want to learn about all these cool things I can do. The problem is that a lot of people end up hurting themselves in the long run because the manipulations only make sense in the context of the system that they're manipulating. And so people don't understand the system or understand what's going on, and they just shoot straight for understanding what the manipulations are, and it doesn't really make sense. And they become crippled because they're dependent upon exploits that are written for programs that were vulnerable 2 weeks ago and now they've been patched. They can't write their own exploits. They don't understand how exploits work. They don't understand why exploits are valuable, right? And so one of the reasons why we're doing this right now is because in Army Cyber and in this whole cyber field as a whole, there's problems where a lot of the leadership that's coming in doesn't really fully understand all the technical details about how all this stuff works. And so they're not able to do their job. This is one aspect. They're not able to do their job as well as they could. Hackers really want to be with technical people. The whole, I'm a leader and let's go for a run, doesn't really hold as much weight with the hacker community as maybe with an infantry community. The other reason why we're learning about all this is because if you learn about this, then all of the tools and programs that use these things are going to be incredibly easy to use, and you'll be able to start doing it on your own. Using a vulnerability that's 2 weeks old isn't as useful or cool as using one that nobody else knows about. Because using one that's 2 weeks old, it's already been fixed and patched, and it's no longer, that vulnerability no longer exists out in the wild, except on probably machines that you're not interested in. If you can find your own vulnerabilities, and you know how to do that, then you can find them before they're patched, before they're fixed. You can possibly have more fun or do a better job protecting America from crazy people outside our borders. Does that paint somewhat more of a picture? This guy right here hates me. He's like, "Rawr." All right, so that's what I learned about assembly. So, in about 2 or 3 more lessons, things should start coming together a little bit more. So I know this is kind of, I don't think it's dry. You might think it's dry because you don't love this stuff with all your heart and soul. Literally, I spent 3 hours in my room yesterday evening just auditing source code because I was bored. So, you know, maybe we have some different interests there. But I think this stuff is interesting. I really like it. But I want you to understand that the reason we're learning is because these manipulations that everybody's really interested in don't make sense if you don't understand the system that you're manipulating. And if you don't understand the system, you can't come up with your own manipulations. If somebody else's manipulation doesn't work, you can't fix it. You're just not as useful, not as capable. It's like trying to fire an M4 if you don't know how a gun works. If you don't know how the M4 works on the inside and you're just pulling the trigger, then if the M4 breaks, you're just sort of pulling on the charging handle hoping that it fixes itself. But when you understand how all the different parts work, you know, the gas comes through the gas tube, blows back the bolt, and you get a better idea of what's going on, you're just more effective. Did you find that file? All right, good. Let's keep going. All right. Let's go back to Ravm. Now we're going to run this program in what I like to call God mode. I call it God mode because you can see all the memory of your process all at once. It's totally cool. All the kids love it. All right. So I'm going to type a /VM for virtual machine. Then we're going to do tac I, or dash I, or hyphen I, however you want to call it. And then we're going to type in the name of our program. If you're wondering how it shows up so fast, if you type in the first couple letters of a file name and hit tab, it'll complete the rest of the file name out as much as it can. So I type in literally like CL, hit tab, it fills in the rest until the dot, because it doesn't know if I want class1.asm or class1.bin. I hit B and hit tab again. So that's how that goes so fast. And the last thing is tac G for God mode. Yeah, get excited. All right, here we go. Hit enter. Look at this. Well, you can't see it yet. Look at that. All right. Let's talk about God mode in the Ravm. So I think right now, if I'm not mistaken, we have 1,024 bytes of memory. Sounds about right. Yeah, okay. So right now we're looking at 1,024 bytes of memory. That's all the memory that's in this imaginary computer called the Ravm, right? And in the Ravm, in this memory, we have our program loaded up here. So remember that disassembled output? Here it is. It starts at address 0. What's highlighted in green is the current instruction that we're executing. So you see down here, the instruction pointer is pointing at all zeros. It's that first address. The instruction is move to and a register 0. Here are all the registers. Register 0 to register 7 are stack pointer or base pointer. What's highlighted in blue is everything that was in our program file, or binary. So right now it's just all instructions. Later will be instructions in beta. We're not going to get into executable formats or formats for executable files, but for the Ravm it's just all thrown in there together. It's pretty awesome, pretty cool. Alright, this is the stack pointer, highlighted in red. We'll get to the stack pointer later. And then if you move around your arrow keys, you get a little cursor in yellow. Alright, and this address right here is the address of the cursor. So if you want to try and find out where something is in memory you don't want to count, you can just move the cursor around till you get there. Makes your life easier. So let's execute an instruction. Alright. To execute an instruction, or to step forward in the program, hit the letter S. Oh man, that was cool. Look at that. Alright, so what happened? Register 0 now holds the value of 2. That's pretty awesome. Alright, so now we're going to add 3 to register 0. Step. There we go. It equals 5. That's pretty cool. Who wants to write a cooler program? I do. Alright. To get out of here, you can just hit, I think you can hit Q, or just hold down Control and hit C. It should clean up all the in-cursor stuff cleanly. Alright, let's write a program that counts from 0 to 9. I don't want to get too crazy, but I think we're ready for this program. All right, and then we'll look at some x86 assembly, and then we'll come back and talk more about the Ravm. All right, so we want to count from 0 to 9. The first thing we're going to need is we're going to need a number that we're counting. So we'll make it R0 again. And we'll set it to 0. Now we're going to need a loop. How many of you know how to program? A little bit? How many of you are no idea? I'm really interested in people who don't know how to program, because normally you learn programming and then come back to assembly. But I've told people this is not the way to go. You should definitely learn assembly first. So I'm really excited to see what happens. So let's talk real quick about how this is going to work. So the first thing we're going to do is we're going to have R0 and we're going to make it equal 0. All right? Then what we have to do is we're going to have a loop. So we'll just have, we call it a label and assembly, but it's just a place in the program that we can go back to later or refer to. All right? So we'll call it loop. Then what we're going to do is we're going to add 1 to R1 or R0, right? Because we're counting. I could probably do this in the program, but I like to board every once in a while. All right. Then what we need to do is we need to see if R0 equals, were we counting 0 to 9 or 0 to 10? Let's make it 0 to 9. Why not? So we need to see if R0 equals 9. And if it equals 9, let's see, do I have a jump less instruction? Jump equal, jump greater, jump 0. Okay. So I don't have a jump less than instruction, so we're going to have a label on here called N. That we're going to jump to when we're done looping. Alright? So what we're going to say is we're going to say if R0 equals 9, then we're going to jump down here to N. So we have what's called a jump instruction. Alright? We just refer to it as J and P. And then right here it goes an address. When we assemble our program, there's going to be a number here that refers to one of those pieces in memory, right? A place in memory where the next instruction is. When we write our assembled program, we just plug a label in here and we let the assembler deal with it later. Alright? So what we want to do is we only want to jump if R0 equals 9. So for us, we have to compare R0 and 9 first. Alright, what does this compare instruction do? So I said briefly that there were some registers in our computer that we didn't deal with directly, that we weren't really that concerned about right now. One of those registers is set by the compare instruction. Flags register, some people might call it something else. Call it a flags register, that's what it is in the Ravm. So it is a flags register. Yeah. Okay. So compare is going to take whatever is in R0, and it'll take 9, and it'll look at the two of them, and if 9 is less than R0, it'll set the flags register to one thing. If it's equal to R0, it'll set the flags register to something else, and if it's greater, it'll set it to another value. All right? We're not really concerned with what exactly the flags register is set to, just knowing that it's set to something else. Then what we do is we call a condition. We have a conditional jump instruction. So the one we're going to use right now is jump equals, all right, J-E, and it's going to take the result of this compare instruction, look at it, and if these two, we call them operands because it sounds cool, but if these two things, R0 and 9, are equal, jump equal, then it's going to jump to an address. The address we want to jump to right here is called loop. No. I'm totally wrong. If they're equal, we want to get out of our program, so we're going to jump to N. Alright? And if they're not equal, we want to keep looping. We'll jump up here to loop. Does this make sense to everybody? Alright? So for those of you who know how to program, it might look something like this. Got it? Alright, let's do it. I'm excited. I can't wait. Somebody in IRC said fun stuff for sure. It's great for my heart. Alright, let's try it out. So what do we have up there? We have move R00. Then we have our label loop. Then I'm going to indent a little bit. I'm going to hit that tab key. I'm going to move it over to the right. I think the tab set for you guys is just a straight tab and it's 8 spaces wide. I don't really like that. When I hit tab, I just like to insert 4 spaces in, so I changed up my editor a little bit. You're free to change it up however you want, but that's why it's going to look a little different. I also think dark colors are easier on the eye, especially at 2 a.m., so I changed up my colors to darker. I usually change them back to brighter colors when I go out in the public because people, you know, think you're weird. But even security professionals think you're weird. Okay, if you could call them that. So what do we have next? Add 1 to R0. Then we're going to compare R0 and 9. Oh, you said that. 9. Okay. All right. If they're equal, we'll jump to end. If they're not, we'll jump to loop. And that's where we'll hold our program. Saved it. Going to assemble it. You're asking yourself, why do I have that class2.bin and then class2.asm ordered like that? The reason is because the assembler will take multiple files for input. And so what'll happen is basically you can have like I have like a string library in there that has some basic string functions, because we'll talk about them later, like string copy. I'm trying to remember, string copy wasn't one of the challenge, but and basically you can use your program and then you can call functions in one of the libraries and then you just add the library in there afterwards. It's kind of cheating, but the assembler will do all that for you, so that's why the assembler is set up this way, in case you were wondering. Alright, want to see if it works? Yes, I do. Okay, cool, let's do it. Here we go. We're back in. Alright, R0 equals 0. You're probably wondering, why do I set R0 to 0 when it's already 0 when we start up? It's good practice. Just always do it. Alright, let's step through. Where are we now? Now we're adding 1 to R0. Now we're comparing R0 to 9. We're jumping if they're equal. Alright, so jump equal 5. Over here I said it was an address. Then we jump to a jump. I lied a little bit. Here it's a relative offset. So 5 is 5 bytes after the end of this instruction. So that's why it's 5 there, even though it's not a valid instruction address, or not the instruction address we would want. Jump -22. There we go. Look at that negative number. That's crazy. Well, maybe we'll talk about why that is later. All right. So we're going to jump 22 bytes back. Oh, here we are, all over again. And we're just going to keep going through. You can actually hold it down if you want. and it'll stop when you get to halt. There's the jump equals 5. Halt. And that is one cool program. Alright. Does anybody else have any simple program ideas? Because if not, we can find prime numbers, we can sort numbers. What else do I have? Or we can just jump straight into the buffer overflow. What do you want to do? You just want to jump straight into the buffer overflow. All right. Let's see here. Straight to the buffer. I'm so disappointed. Okay. So before you guys look at the board and ruin all the answers and fun, let's talk about what this program does. So basically what happens is there's a target value in this program called deadbeat. Alright? And there's a password. And what's going to happen is when the password you enter equals the password, it's going to set this value in memory to all zeros. Alright? So we might return a 1 or return a 0 or do something else, but I said, hey, for here we're just going to set that value equal to 0 because we're not returning anything out of this program. It's just simple. It just shows that if we can find a password that equals password, right, then we'll be able to change the program to do whatever we want with it. Well, if you saw the last Sigsac challenge, the password was randomly generated every time. And the general idea behind that is that sometimes, even when you have programs like this, finding out what the actual password is isn't always the goal. And so for this program, the idea is that we want to write a program where we can get this value set to 0, even if we don't know what the password is. Give me a quick second. All right. So yeah, we're jumping straight into the assembly full time. Oh, you know what we need to do? We should have talked about stack frames before we came to the buffer overflow.
Yeah, man, no,
Guys, killing me. Let's talk about stack frames first. All right, this was totally irresponsible of me to come straight to the buffer overflow. Then we'll talk about the buffer overflow, and then we may even be good for the day. All right. I think the best way to talk about a stack frame, we're just going to look at one in memory as something happens. All right. So we're going to open up the prime.asm program. All right. I'll tell you what it does. So you know what, I'll run it. I'll talk you through what's going on, and then we'll look at the instructions to understand what's going on a little bit better. All right. So we talked about that stack pointer and the base pointer. We move the stack pointer into the base pointer. Why do we do that when they're already the same? We do it because they're not always the same. They are in the Ravm because that's the way the Ravm's made, but don't worry about it. All right, let's move past here. We're going to take the stack pointer, we're going to subtract 40 from it. Alright, that's decimal 40, not hexadecimal 40. Why are we subtracting 40 from it? The reason we're subtracting 40 from it is because in this memory right here, these bottom bytes, we're going to create an array. Alright? We'll have different positions in the array. So if you think about the memory like this, stacked vertically, even though here it's horizontally. All right. We'll say the first piece of our memory is right here at 0. 1, 2, 3, 4, 5, 6. All right, and so these are all going to be integers, 4-byte integers, 32-bit integers, 32-bit CPU, 32-bit integers. 32 divided by 8 is 4. Love that. Okay. When we talk about an array, basically what we're saying is all these different memory locations have something in common. Those of you who know how to program know what an array looks like. Okay, it's like numbers. Zero. All right. When we get into C, you can access elements of an array. You can do tricky things. You don't you do not even need to do the brackets. You can just straight do addition on memory addresses and access pieces of memory, even though that is considered terrible, horrible programming practice, and I would never recommend you do it. You can do it if you want. So the general idea here is that if we are 4 bytes in size, right? And let's say this right here, the real address is 700. And we'll say 700 in decimal, not hexadecimal. This is hexadecimal. If you don't know what hexadecimal is, it's a great topic. Print out the Wikipedia page, do some reading tonight about different numbering systems. You'll have fun. But we're just going to deal with decimal right now. So if num right here, right, points to 700, then you can think of this 0 as 700 plus 0 times 4. All right? When we have 1, when we access 1 in the array, you can think of it as 700 plus 1 times 4, which is going to give us 704, which if this is 4 bytes, it's going to be right there. All right? So what we're doing is we're subtracting 40 bytes from the stack pointer to give us an array of size 10, all right, 0 through 9, and those right there are going to be our numbers that we're going to check for, see if they're prime. So the rest of the program is going to go through, we're going to call a function, and we're going to say, hey, is the number 2 prime? And this function is going to run, and it's going to return a 1 if 2 is prime. It's going to return a negative 1 if 2 is not prime. All right? Let's just run it. We'll look at what it looks like, and then we'll talk about it. So you see the stack pointer moving. You see the base pointer is in purple. You see the instructions are jumping around like crazy all over the place. This more closely mimics what your computer looks like when it runs. All right. So you see, like, wait for it to stop. You see, like right here, these memory addresses, right, even though we're not using them in our program, they're not in any of the highlighted areas, we still have values. All right? When your computer runs a program, you're not guaranteed that all the values are going to be 0 when your program starts running. Okay, it's going to be whatever was there when the program last used the memory. Does that make sense? All right, so that's why when I say you need to zero things out at the beginning of your program, even though all the registers are 0 when the Ravm starts, we still move 0 into the registers. It's just because it's good practice to do that everywhere, all the time, always. All right, so we can start to see here. 2 is prime, 3 is prime, 4 is not, 5 is prime, 6 is not, 7 is prime, 8 is not, 9 is not. And we reached halt, so we're done executing the program. Now let's talk about these stack pointers and these base pointers and how we're asking this function if a number is prime and how this function is telling us whether or not the number is prime. I'm the only one who gets excited for assembly. All right. Let's go back to our program. All right, right here. main, this is the beginning of our program. Right, we move that stack pointer to base pointer, we add -40 to the stack pointer, alright, because you can't subtract constants from registers in the Ravm because I said you can add negative numbers to it, but I didn't want to implement that functionality. Alright, and then you're going to move 2 into register 1. So 2 is going to be the first number we check to see if it's prime. Alright, and then we're going to call this function right here check for prime. Alright, so we don't need to really worry about what check for prime does right now. For those of you who know how to program, and for those of you who know math, you know math, you have f of x equals x plus 1, right? So if x is 3, what is f of x? 4, right? So when we talk about programs, we talk about functions. Okay, x is an argument to the function f of x. All right, and if x is 3, 4, what we get out of f of x is the return value. All right, it's something that the function f of x gives back to us. For check for prime, all right, and then we check to see if a number is prime n. Okay, and then what it's going to do is if n is prime, it's going to return back a 1, and if n is not prime, it's going to return back a -1. Does that make sense to everybody? Okay, how are we going to tell check for prime what arguments we want to pass to it? The way we're going to do that is we have something called a stack. All right. That's why we have the stack pointer. That's why we have a base pointer for stack frame. So we're going to talk about the stack real quick. How are we going to do this? We're going to do it like this. We're going to have 2 functions, a Alright, and B. Alright, here's somebody who has no experience programming whatsoever. Okay. Tell me, looking at this right here, can you tell me what B of 2 is, or B2? 6. Yes, 6. Great. See how intuitive programming is? People say it's hard. It's easy. Okay, let's talk about what this does. We'll start with the function A. Alright? A takes 2 numbers in, it adds them together, and it returns it. Alright? So it returns it to whatever color. So if we say, you know, C equals A 1, 2, we get 3 back. I think we're all solid on this. B takes a number and returns whatever, you know, A n comma 4 is. We're all good. Okay, let's talk about how this is going to look in memory, because this is kind of important. So we're going to start right here. And we're going to have our stack. Look at that stack. Has anyone read Smashing the Stack with Fun and Profit? A little bit of it. I know I sent it out. I'm telling you, read that article. That article is a classic. I know I sent it out a lot last year. I know I sent it out this year. Classic article. It's not on the Army Cyber reading list, and so I just immediately dismiss it. They got like a couple academic papers on there, like a novel. They got some guy who theorizes about the future of cyber war. No, we should be reading Smashing the Stack for Fun and Profit by Halo Point. That is what Army Cyber should be reading. But let's go back. Okay. Here we are. We're in this function B2. Or we're right here. We want to call the function B2. You know what, why don't we just write this program out and assembly and look at it. Ta-da. And we'll run it. We'll talk about what happens. This will be our last class program, and then we'll get into buffer overflow. Let me think here. You're not going to understand all this right now. Just bear with me. How many of you think I can run this and it'll run correctly the first time? You believe in me? Thank you. One person. One person believes. The Ravm? I think towards the end of... Alright. I think I'm done. Oh, I know what I forgot. Does anyone know? ESP. Alright, I think we're good. Here we go. first thing we're going to do is we're going to move 2 into register 0, and then we're going to push register 0 onto the stack. So let's look what it looks like when we push a value on the stack. Alright. So here's the stack, right? Here's value 2. Right now you're thinking that looks like 2 million. And I'm telling you it's value 2. x86 is a little Indian architecture, right? There's big Indian architectures and there's little Indian architectures. The difference is how they order the bytes and their architecture. So if you have a big Indian architecture, race over here. This is important. Like if you read Smashing the Stack for Fun and Profit, he's going to say, and then you want to put the address, 08. Market sucks. 0804, 2222, and then in the middle of the shell code, he's going to go. There you go, that's backwards. Why did he do that? The reason is because x86 is a little Indian architecture. This number right here, right? Remember we talked about hexadecimal, and how each one of these was a byte? Find it. Go read about hexadecimal numbers. You'll be so happy you did. Alright? Here's the short story behind hexadecimal numbers. They go 0 through 9. A, B, C, D, E, F. Why is that? 10, 11, 12, 13, 14, 15. With the 0 is 16 different possibilities for one of these characters. Alright? 2 to the power of 4, 16. Stick 2 hexadecimal numbers next to each other. You get 16 times 16, or 2 to the power of 4 times 2 to the power of 4, which is 2 to the power of 8 different possibilities, which is 1 byte, nicely, neatly, and concisely, in 2 characters. I don't understand how you guys don't find this stuff trivial. It really escapes me. Okay. So that right there, some things are easier when they're ordered little endian. When you start doing things with binary, some things are easier when they're big endian. It's just a matter of choice. The PowerPC architecture used to be used in Macs. Was when I graduated from high school in 2005. I think it's still used in the PlayStation 3. Is that right? The cell architecture. Okay. Anyways, it's big endian. It's a big endian CPU. The Ravm would have been easier, if I remember correctly, would have been easier to implement big endian, but I went back and I made sure it was little endian so it will better represent our x86 architecture. So here, we see the value of this number, and the value is 2, right? And when you take your number and you add 1 to 2 and then you print it out, you're going to get 2 as the value. But the way it is stored and represented in memory is going to be little endian. Are we following so far? Yeah? Fun fact, if you program, you can open files in like mode R and then mode RB for binary. Does anyone know that? No one? One person? The difference is that if you, like a program in C, you open a file in just R mode and then you read it into an end, then it's going to adjust for the endianness. If you open it up in like just read binary mode, it won't make any adjustments. So if you were to do this, if this was ordered in big endian and you were to read it in like RB for read binary in x86, then you would not get the result you wanted. It's cool stuff. It's great. I love computers. All right. So we just pushed 2 onto the stack. We are ready to call a relative and address 7 bytes ahead of us. Let's do it. Boom. Zero D goes on the stack. What is 0D? 0D is the return address. Alright? Go ahead, let's disassemble this program real quick to get a good healthy feeling for what that return address is. Zero D is the address after our call executes. So when the next function returns, yep, see there's a nice instruction, right? When function B returns, the program has to know where to go back to execute the next instruction, because it's not going to execute this. This is the beginning of function A. So what happens is it's going to know where to return to, because it's going to see that return address on the stack, and it's going to set our instruction pointer, right, which is the other special variable that I didn't want to talk about earlier. But basically, instruction pointer just points to all these memory locations. So it points to, 0021, and then we go to the next instruction, and then it points to 0024, 0028, 002D. So what happens is when we return, right, we should have this return address on top of the stack. The computer will pop it off the stack, set the instruction pointer to the return address, and then we'll be ready to execute that instruction. Easier to follow than last class? Yes? Good. All right. Sheeple. Okay. So now we're going to push the base pointer onto the stack. Why do we push the base pointer onto the stack? Well, let's talk about it. We're now creating something called a stack frame. What does our stack frame do? Our stack frame, basically we're going to have, I don't think we actually save any variables on the stack here. So, but this right here, do we execute that, push the base pointer on the stack? All right, 03FC. This right here is the stack frame. We'll call this the base pointer for our main function. All right? It has our argument. It has a return address. It has our base pointer right here. All right? This is the base pointer of the previous stack frame. There is no previous stack frame. Doesn't matter. All right? And then we move the current address of this base pointer into our base pointer. So now, when we want to get to a memory address, let's say here, if we were going to store variables locally in this function, we would store them here. For the prime function, at our base pointer is right here, and then we use an offset from the base pointer. We add 4 to it to get to the first place, and the memory for the function we add 8 to it. We add 12 to it. We can go look at that later. You're going to need to understand that for the buffer overflow thing, I'm pretty sure. But if we want to get to the first argument, then if the stack pointer points right here, we should be able to add 8 to it. I think I put add 4. We're going to find out.
R04.
All right, so this is the first. See what I did. Yep. Give me a second. All right. So this is the first instruction to our B function. Our first argument is 4, so we're going to push that on the stack. All right, move 4 into register 0. All right, and now we're going to try and get that other argument off the stack. I think this worked right. There we go. So now we're going to move the base pointer into register 0. All right. So our base pointer is right here, 3F0. And now we're going to add 8 to our base pointer, which should take us right here. So 3F0 plus 8 should be 3F8. Alright? And now we have this crazy move instruction with the brackets. What do the brackets mean? The brackets mean the value in memory that this register is pointing to. Alright? So right now, register 0 is pointing right here at 3F. It's not right at all. It's completely and totally wrong. See what I did? There we go. Programming and assembly can be difficult and trying on the patients. Alright. 3F8 points to our 2 right here. So now this right here is going to move the value that it's pointing to back into the register. Boom! 2. I'm going to push on the stack. We are preparing the stack frame for function A. Alright. Everybody get the idea for the stack frame? Let's go to return so we can see how that works. So we save some values on the stack. Now we're ready to return. So you see our instruction pointer is at 6.1. Our instruction pointer should go to 3.4 when we're done with this. Are you in IRC?
Yeah.
Ask Mike if he can hear me speaking over the microphone. Alright. There we go. So you see how we push these stack frames onto the stack and then we pop them off, and it allows us to save our state of where we are in the program, and so that we can keep calling functions and coming back and coming back. Everybody got that? Pretty cool. No? You need
You need clarification on something? What? We need help with that.
I'll pause you. I missed first class.
Oh, yeah. You missed first class. You're going to be weird.
Alright. Does everybody understand how we have the arc? Okay. So if you don't understand the stack frame, you're not going to understand the buffer overflow. And oh my god, buffer overflow, stack-based buffer overflow, where we write the return pointer, jump back into the stack, mix key code. Classic. Classic exploitation technique from the early 90s. Many people were pwned until they implemented some exploit mitigation, which we're not going to get into today, but it's like pwn sauce 101. Alright. These are the arguments, and this is the return address, and this is the base pointer. Then right here is where we can store variables in our function. Does that make sense? So let's say we need 1, 2, 3, 4, 5, 6. Let's say we need 6 times 4, 24 bytes of memory to store information in our function, and it's not all going to fit in registers, or we don't want to put it in registers for some reason. After we move the stack pointer to the base pointer, we can just subtract 24 from the stack pointer, move it down to here, and now when we make our next function call, it'll just be down here in the stack, and these memory locations will be okay. Remember how we did that with the prime program? Remember how we added 40 to the stack pointer? You want to see it again? Or you just like show me the creation of this stack frame in the prime program again? Okay. What the hell is going on in IRC? Right there. Boom. Well, okay. I know there's a delay. I apologize. Right there. All this memory right here. We saved for the stack thing. Now, let's say we wanted to store a string in assembly, all right? String in C. The convention that strings are stored in C, we have something called ASCII. If you're on your computer right now, you can just Google ASCII, click on images, you get a whole bunch of ASCII charts, all right? And we have numbers that stand for characters. So like uppercase A is hexadecimal 41, all right? You should see something like that for the character uppercase A. You see that? You see how each letter has a number, and then 0 is null. All right, we call it the null byte. All right, we can represent it like this, But the way a string works in C, the way a string works in our assembly programs is we have a string of characters, and then we have a null byte. When we get to a null byte, we know we're at the end of a string. So let's say we wanted a program where we had a password, right? And you entered a password in. You wanted to save it on the stack. And you would start right here, right? Let's say all this right here from here to here is for our password variable. So,
Is this being recorded on the screen?
I think so. Right? It's 24 bytes. Right there on the stack for our password. Remember, it's 4 bytes for a word, 4 bytes for an integer, word. From now on, when I use those, just assume they're the same thing. Right? So if we start right here, we go A, B, C, R, X, and then we would have a null byte. Imagine for a second that for some reason something went wrong with your program. You did it, and somebody just kept writing. Let's say this right here is address 700 again. Let's say somebody just keeps writing X, 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 700. When this function returns, what's going to happen? The instruction pointer, right, is going to take this return address. The return address is going to go to the instruction pointer. And it's going to execute the instruction right here in the stack. Well, who put that instruction on the stack? You did. You created malicious input for this string to do whatever you wanted, put it on the stack, and instead of having your string null terminate right here, you had it null terminate right after you put in 700, the address of your code. How awesome is that? Okay, that's pretty awesome. If you sort of have some sort of a warm and fuzzy, even a little bit, even if it's a lukewarm fuzzy, that's pretty awesome. All right, Aleph 1 wrote a paper about this called Smashing the Stack of Profit. It is like one of the most famous papers of all time. You gotta read that paper. It will open your eyes to just the joys of. You'll be like, I know now why Alex Eubanks gets so excited for assembly and stack smashing. And then we'll come back and I'll tell you all the things we did to keep people from doing this. And then you'll be sad. And then I'll tell you about all the cool things people are doing to do stuff like this anyway. And then you'll be happy again. But you gotta understand this one first. This one's the most basic. So what does our buffer overflow program do? Well, it works kind of like this. We can actually input into the Ravm from the keyboard because it's a pretty simple virtual machine. All right, I wrote it up in like a week and a half in C. Wrote it in like a week. And then I had this crazy idea for God mode, and I was like, God mode. I took another half a week. All right, so we can't put input in the keyboard. But what we can do is we can say, hey, here's a string. Pretend like somebody just put this string in from the keyboard. And normally you wouldn't actually type these things in from the keyboard. You would read smash in the stack for fun and profit. All right? But that string that we had up there, that string's going to get copied onto the stack. Right? Here, 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 here. And it's just going to keep copying until it overwrites back to 700. All the poor people on the internet aren't getting this high quality education. It's going to overwrite all the way back down here. All right, to instruction we control. Now, unfortunately, because our memory addresses all start with 0000, right? I can't put in the memory address for the location where dead beef is stored. But what I can do, and this is why you should learn about how, as much as you can about computers, when we store negative numbers in a computer, we store them in a certain way to where it's gonna turn out to be, well, I guess you'll see it. This right here, FF20, or this right here, this is actually probably -1, is what this is. All right, that's how we store negative numbers in a computer. So what I can do is I can jump to anywhere I want in the program, right? If it's a negative jump, I can jump anywhere I want and not hit that null byte. So I can continue. So I can put that jump in here, right? And then I just put garbage in the rest of it. And then up here I put the address back down to where that jump was. Function returns, hits my jump. I jump into the program where the program would have gone if the two passwords matched and were the same. And it zeroes out that memory for deadbeat for me. Which, I understand, oh my god, you turned some value to 0 in memory. That's not that cool. But in real programs, not for academic purposes, you can do things like open up a shell and have it connect back to you. Now you control the computer. You can do anything. You own the computer under whatever context that application was running under. So if it's running as the Apache web service, now you're the user Apache on the machine, and you got to figure out that whole mess you're in because you got to figure out how to get to root. If it runs as root because whoever set up that machine is dumb, you're root. If it's a program running your computer, Firefox, somebody writes an exploit for Firefox, you go to that web page, launches the exploit, successfully exploits that computer, that person is now you on your computer. And they probably put their malware on there and everything, and it's all sort of coming together. Stuff like this. Let's look at the buffer overflow.
Mark says he's going to make you some FTP space on the hard.
I have all sorts of FTP space.
Whining that you can't access the image on the FTP address.
Hold on. I know. All right. I gotta assemble them first. See ya. All right. You know what? We'll look at what happens when we run it this way, and then we'll go. All right. So right now the string is test. It will be in a second. All right. So I put the string test in. All right. So let's see if we can find the deadbeat value. Deadbeat. There we go. Right there. All right. So down here, it's all blue, but down here somewhere in memory is our string test. This is probably password. This is probably test. T-E-S-T-S is test, right? So we're going to take test. We're going to move it into memory. We're going to move it around. I'm not going to get into the specifics Alright, we're pushing things onto the stack. And now we're calling a function called string copy. And what you're going to see happen when we call it, it's going to start copying text right here onto the stack. T, E, S, T. Then it's going to hit that null byte, and it's going to say, I reached the end of the string. I don't have to copy anymore. Then it's going to compare the two. The comparison is going to come back false. Run. And deadbeef is going to stay deadbeef. Not very exciting. Now, we're going to take the exploit, we're going to throw that in there. Oh yes. I wrote this in the bays at Camp Buckner during CLDT. How's that for a giant pile of brutality? Alright, here we go. Let's start stepping. Oh, there we go. There's our instruction. That's a jump. That's a negative address. That's actually C3E. Should be right here. EC. This C8, CE. We'll see if it works. Hopefully I haven't messed with the memory too much. Alright. So this right here, what I have highlighted, that's a return address. Alright. Base pointer, return address. Did it go up? I don't care. Alright. Let's keep copying over. What it should happen is it should copy right over the return address just as much as we need, and then we should hit that null byte. Yep. Alright. So I copied it over to 3DC. What you'll see is the location of our exploit code. No one's excited. No one's excited for Ravm. Comes up. Do they match? Oh, R0 is -1. Means no match. You'll see it in a second. That's sad. It's okay. We'll just come back. Remember, even though we're not using it anymore, right here, that memory's still all there. Those values don't change. It doesn't go to 0 when you stop using it. All right, if you write your programs in C and you don't initialize them to 0 every time you start out or whatever value you need, they're just going to be gargled mess because it's going to be whatever was there last. All right. Pop the base pointer off. Let's find that dead beef value. Execute that return statement. Oh, that's cool. Right there. Right there on the stack. Tell you, with people like, can you imagine like if you were like Microsoft, the day you heard about stack-based buffer overflows, overwriting the return address, and just you'd fit so like, let me mute the microphone. Hold on. Where? execute this jump. Negative 962 bytes. Right here. Move the address of dead beef into register 0. Set it to 0. Or something like that. There we go. Boom. Done. Ladies and well, mostly just gentlemen, the buffer overflow. Yeah? A little bit? A little bit excited? Alright, well, I don't know. That's pretty much all I got. I don't know what you guys want to close out with. Maybe some x86 assembly. I don't know. You can take any program in Linux. I mean, there's numerous disassemblers. Pretty much every distribution of Linux comes with one. Just object dump. It's really simple. If you ever want to, like, I don't know, maybe you want to see all the assembly and the Ravm and the disassembler. Which one's the smallest? The disassembler. Well, they're all pretty small, actually. Is it? Come on. It's that D. This. Alright. This little thing right here is going to redirect our output to a file. So I'm going to call it vm.dis. This right here are the instructions for the VM that we just ran. There's a lot of them. Let's keep going down. This right here is something called the oh, it's not the global offset table, it's something else. It's same basic thing. It's for dynamically linking code. That's another day. That's another day. People get them confused. Maybe I'm confused. Oh, here's a function, debug view register. Look at this. Look at this beautiful function right here. Look at that. So see, here we go. We're taking the value, right? That would be the first argument right there, the base pointer plus 8. We're moving it into EBX to register. Alright, we get EAX, EBX, ECX, EDX. So R0, R1, R2, R3. So cool. Here's what the actual instructions look like. Here are the addresses that these would be loaded into memory. Notice there's no 0000 here, which, by the way, is a type of memory protection that I believe Microsoft uses. They try and load their things into addresses so that there's zeros in them. That way, when you can't just have an address in the middle of your exploit because it'll have a 0 in it. Makes it a little bit harder. I mean, you can, but it's tricky. The only way you have to do is you have to have, like, register 0 equals, like some number, and then subtract that number from register 0, and then you get like your 0 there. See how that works? You do some sort of math with the zeros in there, but it's not in the string, so you can copy it over. Yeah, oh, so awesome. Alright, cool. There's some x86 assemblies, so that's what it looks like on your computer. That's all I got. Any questions? No? Excited? You gonna go read Smashing the Stack for Fun and Profit? Yeah? Alright. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have done it. We have scared away 11. We have scared away most of the people here. Alright.